Okay, in this video we're going to talk through starting about 2.1. So we just ended chapter 1 in which you talked about the matrix multiplication by a vector, and we did a lot of ax equals b. Okay, now what we're going to end up doing is, instead of multiplying a vector x times a matrix A, we're going to multiply a matrix A times another matrix. Okay, not necessarily multiplication all the time, maybe adding, subtracting, that kind of thing. And what we're going to get out is a new matrix. Okay, so we're kind of kicking it up a notch, but all of the same properties apply. And so what 2.1 is about is reviewing these operations that we might need to use to compute more complicated things. So first, we can talk about the matrix A in two different ways, in terms of the columns in which each of these things is a vector, A1, A2, all the way up to AN, or we can label each entry, and that's starting with the row and then the column, just like you would if you labeled the matrix M by N. You are labeling each point or each entry as the first row in the first column. Notice that these are all in the first row, so they all have that leading number 1. These are all in the first column, so they have that that secondary number 1. Okay, sometimes you'll hear it referred to as the IJ position. I is for the rows, J is for the columns. Okay, and diagonal entries are exactly what it sounds like, along the diagonal, the ones with the numbers that match. Okay, I think we already know this, but the zero matrix is a matrix whose entries are all 0, just like the zero vector. Okay, you can kind of think about the zero vector as a small zero matrix. Okay, some more definitions. A diagonal matrix is a square matrix whose non-diagonal entries are 0, which means that all of the diagonal entries, A1, 1, A2, 2, A3, 3, would all be some non-zero number. Everything else would be 0. In order for two matrices to be equal, they have to have the same size and they have to have corresponding entries that are equal. So if I have A11, that must be equal to B11. Okay, and in order to add two matrices together, they must be the same size. So I wrote an example here that says we can't sum, notice sum, a 2 by 2 and a 2 by 3. We could multiply those two matrices together because they have matching columns and rows, but I can't add them together. And that's because when we add, we have to add each component to each corresponding component in the other matrix. So you'll notice that I filled these notes out already. That's because we were able to get to this lesson with first period, but I'm still going to come through and talk about each of these things. If you need to pause to kind of look deeper at any of these things as we go along, feel free to. But first, I just want to point out that multiplying a matrix by a constant means that you distribute that constant to each of the components. So if A was 2, 4, the first column was A was 2, 4, the first column of negative 2A is negative 4 and negative 8. Okay. Notice that A and B are the same size, so I can add or subtract them. So if I wanted to do B minus 2A, I'm going to take this matrix and add B to whatever we got over here. And I add each component directly. So 7 plus negative 4 is 3. 1 plus negative 8 is negative 7, and so on and so forth. Okay, so adding two matrices and multiplying by a constant shouldn't feel very different than regular algebra. Okay, we've got a bunch of properties down here. One thing I want you to note, in chapter 1 we had a bunch of theorems, and they were kind of numbered. Like I know we used theorem 4 a lot. The theorems start over in this chapter with numbering. So if you hear theorem 4 again, it's not going to mean the same thing it did in chapter 1. So it's much better to just kind of remember what each theorem says rather than what it's called, unless it has a very distinct name. Okay, so if A, B, and C are matrices of the same size, and we have little r and little s as scalars, then all of these properties apply. So the addition of matrices is commutative. The addition of matrices is associative. Okay, we have the additive identity, zero matrix. I have the distributive property here, and I have the distributive property in the other direction. Okay, and I also have associative with, and notice, sorry, let me clarify, this is distributive with a scalar, and this is distributive with a scalar. and this is also associative with a scalar. Okay, so this is not necessarily true for matrices, or we'll have to talk about that later. Okay, so there's a couple of basic properties. So matrix multiplication is where it starts to get a little bit more complicated. So one thing to point out, if we are multiplying two matrices, the same thing still holds if I need to multiply a vector and a matrix. The number of columns of A has to match the number of rows of B. So this n and this n are the same in order for us to be able to multiply them. Okay, the product AB is the m by p, which notice are the outside numbers here, matrix, whose columns are the matrix A multiplied by the first column in B, all the way up to the matrix A multiplied by the last column in matrix B. Okay, so let's just think about this in a couple ways. First, if A is 4 by 3 and B is 3 by 2, what are the sizes of AB and BA? Remember that the number of columns of A has to match the number of rows of B if we're multiplying A times B. So here you can see that A is a 4 by 3, B is a 3 by 2. The insides match perfectly, so I will get a 4 by 2 matrix. If I do BA though, B is 3 by 2 and A is 4 by 3, I can't multiply these things together because the number of columns of B does not match the number of rows of A. These two need to be the same in order for us to be able to multiply this, so this is not possible. Okay, and here is a nice diagram which you might want to pause and kind of look over as you're going through the notes, and how to multiply A and B together. So the first thing you're going to do, and this is where again you'll see me start to take my hand in class and do a lot of like flipping, okay, because I'm taking the column and I'm multiplying it by the row here. We will get, okay, since A and B, A is a 2 by 3 matrix and B is a 3 by 2 matrix, my answer should be a 2 by 2. Okay, 2 by 2 matrix. So when I multiply the first column of B to the first row of A, that will give me the first entry. Notice that this is A1 and B1. Okay, multiplying those two things together will give me, I guess we'll call it AB11. Okay, so whatever row you multiply by whatever column, those numbers will be the corresponding entry here, if you want to think about labeling each entry as a number. So in order to get 28, here is the first entry of A times B. They did 2 times 2, which is 4, plus 0 times 3, which is 0, plus 4 times 6, which is 24. So 4 plus 24 is 28. Okay? Then they moved on to multiplying the first row by the second column. So this is A1 and B2. So this is the position 1, 2. Okay, to get negative 45, they multiplied negative 3 times 2, 1 times 3, and negative 7 times 6. Okay, negative 45. And then they kept going. Once they had finished with all of the columns that would be multiplied by the first row, they moved on to the second row, A2, and multiplied it by all the columns to get the final entries. So this is our final matrix here. Now, you are allowed to choose whatever direction you want to go. I actually like to just use the first column, and instead of going finding all of the entries in one row, I like to find the entries in all of the columns first. So I actually do this step first, then I do this step, and then I come back and do this and then this. And that's okay. Okay, because each entry is being calculated separately from the other entries. Okay, so you can either figure out if you want to multiply the column times each row first, or if you want to stick with one row and do all of the columns. Either way. Okay, so a couple of examples here at the bottom. Okay, one thing I want to point out, this one is not possible. Notice that ED, okay, multiplying E, which is 2 by 1, times D, which is 2 by 2, is not possible because the number of columns of E does not match the number of rows of D. So we're out of luck. Okay, but let's do just one together. I'll do A, and you can check these other two in the field notes. Okay, if I wanted to multiply C times D, Okay, I set that up here. And I like to write it out always, because if it's listed this way in the when it's given in an example, that might not be the direction I'm going to multiply it in. So I always like to write it out a second time. So you notice I wrote it out here when I'm multiplying D times C. And that's specifically because I like to multiply from the right matrix to the left matrix. So in order to find the first component of CD, I multiply the first column times the first row. So 3 times 1 minus 2. Okay, that will give me 1. And then move down, and I did 3 times negative 2, which is negative 6, minus 1. So I get negative 7. Then I moved over to the second column. 5 times 1 is 5. 4 times 2 is 8. Then I move down. 5 times negative 2 is negative 10. 4 times 1 is 4. Okay, and altogether, this matrix here is CD. And I can check to make sure this is the right size, because C was 2 by 2, and D is 2 by 2. So multiplying them together should give me a 2 by 2 matrix. There it is. Okay, here are some properties. Every time we introduce a new operation, we have to talk about the properties. So I've labeled these here for you a little bit, but here you can see that the associative law for multiplication is true. Okay, so I could multiply BC and then multiply it by A, or multiply AB and then by C. Notice that the order is still ABC, ABC. And that's because down here, you'll notice that commutative multiplication is not held in this, sorry, let me say that again. The commutativity of multiplication is not valid for matrices. You can't multiply them in opposite orders and get the same thing. If you could, that's something special we'll talk about in a further lesson. Okay, I could do distributive law from the left side. I could do distributive law from the right side. Notice though that the order stays the same. If I multiply from the right side, it's BA, CA. If I multiply from the left side, it's AB, AC. Okay. You can also multiply a scalar in, that's totally fine. And then the identity matrix, don't forget, is the matrix with all ones along the diagonal, and everything else is 0. Okay, so that's the identity matrix. Other warnings. You cannot divide. So if AB equals AC, you cannot say then B equals C. That's not true. Okay, you can't divide by A. You can do the inverse of A, which we'll talk about in the next lesson, but you can't divide by A. Okay, and if AB is equal to 0, you can't conclude that either A is 0 or B is 0, and I've provided an example for you here. Okay, the zero product property is how we used to find roots in polynomials. If I had like x plus 2 and x minus 3 equals 0, then you assumed like, oh, well, one of them must be equal to 0, one of them must be a root. That is not true for matrices. Okay. For example 4, I'm going to skip over it just a little bit, but you can see it in the field notes. I want you to find the non-zero matrix such that multiplying A by that matrix is equal to 0. There is definitely more than one answer. Okay. All right, exponents. The one thing you need to know here is that we do not distribute that exponent into each entry. Okay, you actually have to multiply it out 3 times. And we know that's the definition of exponents. We're multiplying over and over and over again, but we can't distribute this. And so if I multiply the first two together, I got this matrix, 1, 0, 9, 4. And if I multiply it again, I get 1, 0, 21, 8. So even though it looks like I was like, okay, look, I multiplied 1 cubed, 0 cubed, 2 cubed, this last one doesn't really apply. This 21 is not close enough to being 3 cubed. So make sure that you don't distribute the exponent to each of the entries. Okay, last page. New definition. The transpose of a matrix. Okay, and since we're going to get into inverses in a little bit, we want to make sure that your notation is good here. So if you're talking about A transpose, it's A, kind of looks like to the T power, but we're just saying A transpose. We have switched the columns and rows of A to get the transpose. So A and A transpose are not the same dimensions. Okay, so notice that here, A was a 3 by 4 matrix. A transpose is a 4 by 3 matrix. Okay, because we switched the rows and columns. Okay, and that means that if this was row 1, it is now going to be column 1. If this is row 2, it's now going to be column 2. You can think about it that way. Or you can think about each of the columns of A becoming the rows of A transpose, whichever way you would like to think about it. There are a couple of properties here, okay, that you'll need for the rest of the examples. If I do the transpose twice, I am back at where I started. Okay, that makes sense. If I switch 3 by 4, I'm going to get 4 by 3, and then I switch this, I get back to 3 by 4. I've just switched the rows and the columns twice, resulting back in the original matrix. Here, the second property says that if I sum two matrices and then take the transpose, that will be equal to the sum of the transposes. So I could just take the transpose of them separately and then add it together. Okay. If I have a scalar, I can factor it out before I take the transpose. And one final important thing, if you multiply two matrices together and get the transpose, and then take the transpose, that is equal to taking the transpose of both matrices and multiplying them in the opposite order. Okay, that's a little confusing, but I've written that statement here for you in case you need to copy that down. Okay, so again, if I take two matrices and multiply them together, and then take the resulting transpose, that would be equal to if I took their transpose separately and then multiply those two matrices in the reverse order. Okay. So one thing I want to point out, when you're doing these practice examples down here, okay, and this will be our practice, definitely do this by hand. Okay, I don't think you can do this in your calculator. You can think about AB transpose as the same as B transpose A transpose, okay, which is the same as part C. Okay, I actually recommend trying it out for yourself both ways, okay, just to make sure you get to the same matrix in the end. Maybe just on some scratch paper, it doesn't have to be in part of your formal notes, but try it both ways, see which way you find easier. Okay. This one is a little bit tricky, okay, because one, I will need to find A transpose, B transpose, multiply those two things together, and then square it, meaning multiply it by itself, which is a lot of work, but, okay, you need to start practicing this. So think about all those times you didn't do row reduction in your calculator. Here it is, coming back. Notice we're not doing row reduction, we're just doing some math by hand. Okay, and if it helps, what I've written here is the intermediate steps before I added them, like combine these numbers together to get the next matrix. So that way I knew what I was adding and what I was subtracting later. Okay, all right, one more proof. Okay, I would like you to try this if you can. All right, prove that multiplying three matrices and then doing transpose is the same as taking each of their transposes and multiplying them in the opposite order. Okay, I've left you a hint here. Use part D of theorem 3, and also that matrix multiplication is associative, meaning try to associate some of these together to see if you can get back to where you began. Okay. All right, that's it for 2.1. That's it for 2.1.